Hello students, today we'll talk about uh, Coulomb's law and how to use Coulomb's law if you don't have 2 point charges. You have 1 point charge and other charge distributed on some line or over some surface or over some volume. So can we find out force between two charges in such situation? Can we use Coulomb's law for this scenario? So today we'll try to understand it, if we can use Coulomb's law or not, and if yes, how to use it. So let us start. To understand today's topic, we'll need to know vector form of Coulomb's law and its vector form both. I assume that you know the Coulomb's law, statement of Coulomb's law, that it is the electrostatic force between two stationary point charges, and it can be given as k q1 q2 by r square. This is scalar form of the electrostatic force, and if you want vector form can be given as FAB as 1 by 4 pi epsilon 0 QA QB vector RA minus RB mod RA minus RB whole cube. What is RA? What is RB? RA is position vector of QA and RB is position vector of second charge QB. So this is what you are supposed to know, and if you have any doubt, you should go back to video of Coulomb's law and its vector form before continuing with the current topic further. So assuming that you know this, let us start with today's topic. Consider a point charge Q and another charge capital Q distributed over some line, and we want to find out force between these two charges. Now, as they are charges, there must be some force, maybe attraction or repulsion. The problem is how to find out force between the two. Because when you try to find out force, if you look at distance of this part of line from point charge, or this part of line from point charge, or distance of this part of line from point charge, the distances are not same. And so if we try to find out with k q1 q2 by r square, you have different values of r. Different parts of the line are at different distances, and then it is not possible to find force in one step with Coulomb's law. So what is the way out? The way out is, instead of applying Coulomb's law for total charge Q, take small part of line. Let us say this small part if we choose. Now whatever is this charge on this small part can be considered as point charge, and if this is the point charge, if this is the point charge, we should be able to find out force between these two. And then we'll find out force on other small part, force due to other small part of line, and that is how we'll divide the whole line into small parts, and we'll find out force on Q, point charge Q, due to all the small parts, and then we'll sum up. So that is the logic, and with that logic let us proceed further. So I have chosen small part of the line. How much is the length of line? Say dl. Where you have chosen the small length, small line segment, so we say that our point charge Q is at position vector r, and the chosen line element is at position vector r prime. So now I have one point charge Q. Where is the other charge? dq here. How much is the dq? Do you know how much is the charge value here? We have chosen length, maybe 1 centimeter, 1 millimeter, but it is length. How much is the charge on that length? So let us first find out how much is the charge on dl. So we'll employ simple logic that if total length is having total charge, small length is having how much charge? So total length L is taking care of total charge capital Q, small length dl will have charge Q by L into dl. This is what I have on small length dl. So this is my 1 point charge, here is my another point charge. I have two area vectors, position vectors. I should be able to find out force. But before that, here we have one new quantity appearing. Q by L is actually line charge density, which is symbolized by lambda. And if we replace q by L with lambda, dq becomes lambda into dl. Lambda into dl. And what is the unit of lambda? It is q by L, so Coulomb per meter. So what is the step next? Now first I'll find out force between q and dq. Let us try to find out force between q and dq. So we apply vector form of Coulomb's law. This is first charge, second charge. I want force on q, so position vector of q will come first. If you want force on dq, it should be r prime minus r, but right now we want force on point charge, so r will come first. What is df? Df is force. Force on what? Force on q. Force on q due to what? Force on q due to small part of line or charge on small line element. Okay, so now we know dq value. Dq is lambda dl. So let us substitute and let us rearrange. Okay, so this is what we have now. We got force on q, but not due to whole line. We got force on q only due to small part of line or line segment. To get total force, we integrate both sides. And this is what we have. Now left side is integration df, so I'll get total force. I'll replace it with vector f. So this is the expression of force we are looking for. What is F? Force on small charge q due to line charge distribution with line charge density lambda. With one assumption, we have made one assumption here. This logic is applicable only when you have charge uniformly distributed. So suppose if you have 5 meter long line and say 10 Coulomb charge distributed on it. What is the charge per unit length? So we say that 5 meter is having 10 Coulomb, 1 meter will have how much? So 10 by 5, that is 2 Coulomb charge is distributed on every meter of the line. But here we are assuming that the distribution is uniform, which is not the case always. So if charge distribution is not uniform, this equation will be changed slightly and it can be written as this. Compare the two. The only difference is here. What it shows that you are talking about lambda line charge density at point r prime, which is not the case here because lambda is constant everywhere. So what is this f? What is this f? It is the force on given point charge due to line charge distribution which is not uniform. And what is this f? It is force on point charge q due to uniform line charge distribution. Okay, so now let us move to second possibility where charge may not be distributed on line but it is distributed on some surface. So again we have point charge q and other charge capital Q distributed on some surface. Say this is the surface on which our capital charge Q is uniformly distributed. And again we want to find out force between the two. So again we'll choose small part of the surface. We'll find out force on charge of that small part and point charge and then we'll integrate. So let us consider small part of area, say area element dA of the surface, and we'll consider charge here to be dq. So where you have chosen your area element, we say that point charge q is at position vector r and the area element is chosen at position vector r prime. How much is the charge on the area dA? So again simple logic we apply that total area is having total charge. So charge on small area dA. Charge on small area dA can be given as q by a into dA. dq is equal to q by a dA. Now here again q by a is charge per unit area, which is called surface charge density, and it is symbolized by sigma. So if we replace this q by a with sigma, we have dq is equal to sigma dA. And what is sigma? Surface charge density, what is its unit? Coulomb per meter square. So now we have dq, charge in the small area, we have other charge q. We should be able to find out force between the two because we have position vectors also. So let us first find out force on point charge q due to charge on small area element. I will call it df. So applying vector form of Coulomb's law, we get this equation. Again, I would like to highlight that r you should consider first because we want force on point charge q, so its position vector will come first. Now substitute dq value. What is dq for now? It is sigma dA. So after substituting, this is what we have, and I'll rearrange the terms. Okay, what now? Now I have force on point charge due to small surface element, but I want total force. What to do to get total force? Integrate both sides. So now I'll integrate on left side and right side, and here I need to be careful that I am integrating over surface, so I must mention area here, that this is the integration over area, so I'll have to mention it, unlike previous case where integration was over line. So there we had limit 0 to L. In this case we will have to mention that integration is over area. Now left side will be F, integration of df will give us F, right side will remain as it is, and this is what we have as expression of force. What is F? Force on point charge q. Due to what? Due to uniform surface charge distribution. And what if charge distribution is not uniform? What if you have more charge here, less charge here? In that case, sigma will be varying. Sigma is not constant, and then you will have to indicate that sigma is function of position r prime. So this is the only difference, just like previous case. If the charge distribution is non-uniform, mention sigma r prime. If charge distribution is uniform, simply mention sigma. No other difference. Okay, so let us move to third possibility where charge may be distributed in some volume. Consider that again our point charge q is placed near some other charge capital, and the capital Q is distributed over some volume, and we want to find out force between the two. As this is distributed charge, Coulomb's law cannot be directly applied, so we'll choose small part of the volume. We'll call it volume element. Let us consider volume element dV. We'll find out force between Q and charge, whatever we have here, we'll indicate it by dQ. But first we'll have to mention where we have chosen volume element. So again, point charge q is at position vector r, and volume element is chosen at position vector r prime. How much is the charge in your chosen volume element? So again, simple logic, total volume is having total charge, small volume will have how much charge. So I can say that dq is q by v dv, and once again q by v is charge per unit volume. It is a quantity which is symbolized by Greek alphabet rho. So instead of q by v, if we take rho, dq can be written as rho dv. What is rho? Volume charge density. What is the unit of rho? Coulomb per meter cube. So now we have dq, which can be considered as point charge. Q is already point charge, so we should be able to find out force between these two. So first we'll find out force between dq and q, and then we'll integrate to get force on q due to total volume charge distribution. So applying vector form of Coulomb's law, we get this equation q1 q2 by r square, but as we have direction, we have vector upon r cube. And substitute dq value. So instead of dq, we can write rho dv for present situation, and we'll rearrange the terms just like previous two cases. What next? What is this df? Force on point charge q due to charge in volume element dv. To get total force, integrate both sides. So this is what we have. Again, compared to previous case, here we have volume, and it is being integrated over dv, small volume element. Left side will be F. So this is the force on point charge Q due to uniform volume charge distribution. This rho is assumed to be uniform. What if charge density is varying? What if charge distribution is not uniform? In that case, instead of writing rho, we should write rho of r prime. So this last equation is giving us force on point charge due to non-uniform volume charge distribution. This is also force on point charge, but this is force on point charge due to uniform volume charge distribution. So that is how we can find out force on point charge due to different charge distribution. Let us sum up. So if you have line charge distribution, first thing we need to know is how much is the line charge density, which is lambda given as Q by L, and unit is Coulomb per meter. How much is the force on point charge due to line charge distribution? The force on point charge due to line charge distribution can be given as this. We are integrating over line, so limit is 0 to L. Who is integrating? DL. And we have lambda r prime, means we are talking about non-uniform line charge distribution. What if you have uniform line charge distribution? Simply write lambda here. Second possibility is charge may be distributed on some surface. So in that case, we need to know how much is the surface charge density. So first find out sigma, which is Q by A, unit is Coulomb per meter square. And how do we express force on point charge due to surface charge distribution? So that can be expressed as F is equal to 1 by 4 pi epsilon 0. And integration over area, look at this. Here we are integrating over area by dA, and here we consider surface charge density. R prime is mentioned, so we are saying that we are talking about non-uniform surface charge distribution. Otherwise, omit R prime. And very similar is the third case, volume charge distribution. If you have, first find out volume charge density, which is sigma is equal to Q by V, unit is Coulomb per meter cube. And force on point charge due to volume charge distribution is again very similar to this two, except integration is now over volume. dV is integrating the term, and we have volume charge distribution. So, sorry, volume charge density here. So this was the topic today. I hope you understood this, and we keep it up to this for now. Thank you.